Then I would like to invite the next speaker, Dr. Soonseok Song. He's a research associate at the University of Strathclyde, and today he will be presenting the results of a very interesting project. Dr. Soonseok Song, the floor is yours.
Thank you very much, Dr. Demirel. So, hello everyone. My name is Soonseok Song, and I'm a research associate from Strathclyde University. And today, I'm going to talk about economic and environmental impacts of different anti-fouling strategies for fishing boats in Turkey. So, around the world, there are approximately 36 million fishermen working on small-scale fishing boats. And traditional design and materials are inefficient and may waste a substantial amount of fuel. And inefficient anti-fouling strategies accelerate the accumulation of biofouling. And what is biofouling? Biofouling is unwanted growth of marine organisms on the surfaces of submerged or semi-submerged objects, such as slime, seaweed, barnacles, or mussels. And these can be easily found on the surfaces of ship hull and marine propellers. And once the surface is fouled, the surface roughness increases, and there are many consequences. So increased surface roughness can result in increased ship resistance and also decreased propeller efficiency. So these effects can result in economic and environmental penalties. And to mitigate such penalties, we need anti-fouling activities such as hull cleaning, dry docking, and anti-fouling coatings, and etc. But the problem is these anti-fouling activities are very expensive. So that is why we need a proper smart anti-fouling strategy. For example, we need to find the best combination of marine coatings, hull cleaning procedures, and operational characteristics. So in this context, life cycle assessment is of paramount importance. That is because by LCA, we can compare the pros and cons of different anti-fouling strategies. So we can directly compare the penalty of biofouling and also the cost of biofouling. So life cycle assessment considers the ship's operational profile and biofouling growth on ship's hull, and finally the penalty of biofouling on ship's performance. So the aim of this study is to investigate the economic and environmental impact of fishing boats in Turkey with different anti-fouling strategies and also in different fishing regions in Turkey. So objectives are first to adopt time-based biofouling growth model for Turkish fishing regions, and also to predict the biofouling growth on fishing boats with different anti-fouling strategies. And finally, to predict the impact of biofouling on ships' hydrodynamic performance and therefore the economic and environmental impact. So we used the time-dependent biofouling growth model developed by our previous work. So this growth model predicts the fouling ratings of on the self-polishing copolymer type anti-fouling coating. So this SPC type anti-fouling coating is the most popular anti-fouling coating for fishing boats. So to predict such fouling rating, so by the way, fouling rating is the level of fouling severity. So we need to predict such thing. We need annual average seawater temperature of the fishing region and also the operational profile of the ship as an input. And output we can get is the fouling rating of the slime and also fouling rating of the non-shell organisms, as well as the surface coverages of the calcareous fouling. So we adopted this model. For Turkish fishing regions such as Black Sea, Marmara Sea, Aegean Sea, and Mediterranean Sea. So basically, we calculated the coefficients of such a mathematical model, the time-dependent growth model. So we interpolated such coefficients such as A, B, or like B, C here, F, G. So we calculated the coefficient for the Turkish fishing regions. And finally, we could get the equivalent centigrade roughness height for the fouled surfaces using the method developed by Uzun et al. So for example, here you can see that the KS, the centigrade rough, equivalent centigrade roughness height is the, as the name suggests, it is the centigrade roughness height which gives the same increase of the hydrodynamic drag. So like different fouling surfaces. So if the fouling level increases, basically the KS number increases. So from the methodology of Uzun et al, we adopted that to 4 Turkish fishing regions, and you can see that with different static immersion time, you can see that the KS value increases. So with this KS value, we can calculate the impact of the surface on ship's hydrodynamic characteristic, either by using similarity law analysis or computational fluid dynamics. And in this specific study, we are using the similarity law analysis to calculate the added resistance to roughness. So we used the similarity law scaling method of Granville. This method is based on the turbulent boundary layer similarity law, and this can predict the skin friction of a flat plate with arbitrary length and speed. And it assumes the uniform distribution of the given rough surface, and this method is quick, robust, and ensures good agreement with other high fidelity methods, including the CFD simulation. So in our previous studies, we validated this method against CFD and also against ship model test. So we are going to use this method. So these 2 vessels are our objective vessels, so 8-meter fishing boat and 20-meter fishing boat. And also we considered 6 different anti-fouling strategies, including hull cleaning conditions with different frequencies, 1 year to 5 year, and no cleaning and hull grooming. And hull grooming means it's a frequent mild hull cleaning rather than cleaning the hull entirely. So so this strategy is just to avoid clean it mildly before the biofouling settles down onto the hull. So using our methodology, we first generated the KS numbers of the 8-meter fishing boat in 4 different fishing regions, Mediterranean Sea to Marmara Sea. And you can see that different anti-fouling strategies basically give different KS growth on the hull. And as expected, no cleaning condition shows the highest KS values, while the grooming condition shows the smallest KS value. And we did the same for the 20-meter fishing boat, but the difference is for the 20-meter fishing boat, we also consider the fishing ban seasons every year. So we calculated the KS growth on the ships over the 20 years of operations. So from the calculated KS values, we also calculated the delta CF, the added frictional resistance using the similarity law scaling method, as I mentioned. And then with that, we finally calculated the increase in the effective power of the ship. So you can see that we finally produced the percentage increase of the effective power of the fishing boat. So you can see that it goes up to more than 50% if no cleaning is conducted, and you can keep it less than like 3% if hull grooming strategy is used. And we did the same for the 20-meter fishing boat. So once we have the increase in the effective power, we can estimate the increase in the daily fuel consumption. And if we know the daily fuel consumption, and also if we have the operational profile, we can also estimate the cumulative fuel consumption over the lifetime. So even if the difference is small daily, it can reach to big difference at the end of the lifetime of the fishing boat. So we calculated such things for 8-meter and 20-meter fishing boat. And finally, the difference is like this. So this shows the total fuel cost. So we simply calculated the fuel cost by multiplying the amount of fuel consumed and the fuel price. So for example, you can see that no cleaning condition shows the largest fuel cost, and it shows that up to 70,000 pounds sterling can be saved if you use a proper antifouling strategy for the 8-meter fishing boat. And when it comes to the 20-meter fishing boat, we can save up to 440,000 pounds sterling if a proper antifouling strategy is used. And also, because we have the fuel consumption estimations, we can also estimate the CO2 emission from the fishing boat. So this is the total CO2 emission of a 8-meter fishing boat. So you can see that up to 380 tons of CO2 can be saved from one single boat over the lifetime. And when it comes to the 20-meter fishing boat, you can save 2,400 tons of CO2 emission from one fishing boat over the lifetime. So as a conclusion, so economic and environmental impact of different antifouling strategies were analyzed. So different ships were considered for 20-year operations, and different fishing regions, and finally different hull cleaning practices. And fouling growth model was adopted to predict the fouling growth on the fishing boat, and we considered the operational profile as well as the climate of different fishing regions. And finally, engineering, economic, and environmental calculations were carried out, and these includes the impact of fishing boats, energy efficiency, increase in the fuel consumption and fuel cost over the lifetime, and finally the CO2 emission over the lifetime. So future work. So in this study, we studied the very specific fishing regions, and also we also studied the impact on the very specific fishing boat. So this same methodology can be extended for example, for different different vessels, like other commercial vessels or like warships, and also for different climate or different operational profiles. And also, this methodology can be improved for better accuracy. For example, we can somehow consider the like time-dependent like changes of propulsion efficiency for better prediction. And also in this study, we used some simplified assumptions. So we didn't really consider the heterogeneous distribution of the biofouling on the hull, but in the nature, it is known that the biofouling accumulation of ship's hull or propeller is not homogeneous. So we can consider the like different heterogeneous, we can maybe develop a time-dependent growth model for heterogeneous hull roughness. And also we studied the SPC type coating only, but we can also like widen the scope for different surfaces or coatings. So I would like to acknowledge our research project, so SFC project, development of smart antifouling strategies toward energy efficient fishing boats in Turkey, and also the EU Horizon 2020 project venture. So that is all from me. Thank you very much.
Many thanks for your presentation, Dr. Song. It
Thank you
was
very much.
very interesting.